Okay, so for Unit 3, we are actually getting into kind of the heart of what the purpose of this class is, and that is our dosage calculations. There is some background that we need to know before we get into those dosage calculations. When we talked about ratio and proportion, one ratio that we had mentioned was something called the dilution. And a dilution is a ratio of parts of concentrate to total parts of solution. So the word dilution kind of describes it. It is you taking either a pure medication or a concentrated substance and you are diluting it down. What the concentrate could be a medication, or it could be blood, a blood sample, a urine sample, or anything like that that gets diluted down for whatever purposes. A lot of times we're going to be referring to that concentrate as serum if it's a medication. So the first thing we need to look at is we need to look at the structure of this ratio and some of the things we can pull out of it. So let's say that we have, well, first of all, let's say we put 2 milliliters of serum, so it's a medication, into a 10 milliliter total solution. So what that is saying is after we put in the 2 milliliters of the medication, we have 10 milliliters of total solution. So that dilution is 2 milliliters in 10 milliliters. Now it's very important that the units are the same. Remember, in a ratio, the units must be the same so that those units will cancel out. So the milliliters cancel out. 2 and 10, well, both of them can be divided by 2, which gives me a 1 and 5. So this would actually be referred to as a 1 in 5 dilution. Now, similar to that, we might combine 30 milliliters of medication, so 30 milliliters of serum again, with 120 milliliters of, and the abbreviation NS, again, stands for either neutral solution or normal saline. It's basically all it is it's sterilized water that has no medicinal value. If I want to find the dilution for this, well, we have 30 milliliters of our serum. That's our concentrate. What goes into the denominator here, though? 150. Very good. How did we get that? We had the 120 milliliters. That's just of the water that is added to the 30 milliliters of the serum. So we have to add those together. So the milliliters still cancel out, but this is 30 over 150. Both of those will divide by 30, give me 1 in 5 again. So this is also a 1 in 5 dilution. We might have a situation where 240 milliliters of solution is created after adding 210 milliliters of water, of NS, to the serum. Once again, find the dilution. So we have 240 milliliters of solution. So that would be the bottom number in our dilution. What's supposed to describe the top number? The top number is supposed to be parts of serum. Okay, where did the 30 come from? Perfect. Yeah. Total is 240 milliliters. That includes 210 milliliters of water, of normal saline. So that means the difference, 240 minus 210, is 30 milliliters of serum. We're assuming that there is no dissolving effect here where the volume does not reduce because the particles disappear within the particles of the other liquid. So anyway, we've got 30 over 240. Again, the units disappear. Both 30 and 240 can be divided by 30. 30 divided by 30 is 1. 240 divided by 30 is 8. So this is a 1 in 8 dilution. So as you can see, there are always 3 ratios present in these dilutions, and we can use those ratios to find the other pieces. For example, in this situation, we were actually given the ratio, or we're given the amount of the normal saline and the total amount of solution. So we could have done the ratio of NS to total solution, which was the 210 to 240, or a 7 to 8 ratio. Up here, of course, we did the serum to total, which was the 30 to 240, or the 1 in 8 ratio. There's also a ratio of serum to water. And of course here, we've got the 1 part serum. 8 minus 1 is the 7 parts water, which we could have got from this ratio as well. So there's the 1 to 7 parts of serum to saline. So if we come at this from a different angle, if we are told that we have a 2 in 11 dilution, find the ratio of serum to water. So we've got that 2 in 11 dilution. What does the 2 represent there? That is the parts of serum. Good. What's the 11 represent? Yes, that is the total parts. So we want the ratio of serum to saline, serum to water. So the 2 represents the serum, but the 11 does not represent the water. So if I want the ratio of serum to my normal saline, can I still use the 2 for serum?
Yes.
Yes, I can. What has to go in for the saline or the water? Yeah, 11. Go ahead. Yep, exactly. We have 11 total parts, 2 of them serum. 11 minus 2 has to be 9 parts of saline. So that would be a 2 to 9 ratio of serum to saline or serum to water. So let's say we have in a 3 in 8 dilution, of serum and water, how much serum is needed to create 240 milliliters of solution. So we've got the 3 and 8 dilution again, and I like to label things out. The 3 still represents the serum, and the 8 represents the total solution, total parts. You got it. So looking at this, we're asked how much serum is needed. Well, that is what's being described on top. To create 240 milliliters of solution. Is that total solution? Yes, it is. Good. So that 240 milliliters can go on bottom. So what we had here, the information in the dilution is the information we needed for this problem. So now we'll just go ahead and cross multiply and divide. 3 times 240 divided by 8 is, what is that, 90 milliliters? So we need 90 milliliters of serum to create that dilution. Similar to that, let's say we have a 2 in 7 dilution. I want to know how much solution can be created using 50 milliliters of serum. So again, we'll start out with the 2 and 7. The 2 again represents the parts of serum, and the 7 is the total parts of the total solution. So here we have the 50 milliliters. That is describing the serum, so that's going to go on top. Is the number we're looking for, does that describe the total solution? Yeah, it says how much solution can be created. So that is the total solution that we're looking for. So that's our missing number. So we'll cross multiply and divide. 7 times 50 is 350. Divided by 2 is 175 milliliters. So 50 milliliters of serum can be used to create 175 milliliters of total solution there. So let's say we have a 1 in 4 dilution of blood in water. So blood in normal saline. How much NS is needed to mix with 30 milliliters of blood? So we've got the 1 in 4, that's our dilution. And of course the 1 is the serum, or in this case, the blood. The 4 is total parts again, so total solution. So now here, we have 30 milliliters of blood is given. So that would go with the blood. Are we looking for the total parts? No, we're asked how much water, how much of that normal saline is needed. So we're not looking for the total parts or the total solution here. So we have a couple of different options. We could find this number here and subtract. Let me go ahead and do it that way quick. 4 times 30 is 120, divided by 1 is 120 milliliters. Oops, milliliters. Subtracting there would be 120 minus 30. Would give us 90 milliliters of saline. The other way we could have approached that is we could have created that ratio of blood to water, or blood to saline. It's still 1 part blood, but how many parts of water is there going to be? 3. Where did 3 come from? 4 minus 1, right? There's 4 total parts, and 1 of those parts is blood. 4 minus 1, the other 3 parts have to be the water. And now on the other side, the 30 milliliters still describes the blood. And we can cross multiply. 3 times 30 is 90, divided by 1 is 90 milliliters. So either way, we get 90 milliliters for the amount of water or saline that's added to that solution. Sometimes we don't have the option of doing it either way. Sometimes we're given a problem like this in a 5 and 12 dilution. How much serum is mixed with 140 milliliters of normal saline? Well, again, we have a 5 and 12 dilution. The 5 describes parts of serum. 12 describes total parts of total solution. Now, we are looking for the amount of serum. That's what we're looking for. But we do not know the total amount of solution. So in this case, we're missing both of the numbers over in this side of that proportion. So we cannot solve that proportion. So that proportion won't work. So what we're going to do is we're going to create the proportion, the ratio, I should say, of serum to saline, or serum to water here. We still have 5 parts serum. How many parts of water do we have? Careful. The 140 is the total parts. That's going to go over on the other side. But in our ratio from the dilution, what was that? 7, yes. 12 minus 5 gives us 7. Because there's 12 total parts in the dilution. If 5 of those parts is serum, the other 7 parts have to be water. Now, over on the other side of this ratio, you're absolutely correct. We have 140 milliliters of water. So that goes there. And we are looking for the milliliters of serum. So now we cross multiply and divide. 5 times 140 is 700. Divided by 7 is 100 milliliters. So there would be 100 milliliters of serum here added to the 140 milliliters of water to create that solution. In a, now let's say we have a 4 in 15 dilution of blood in water again. How much water, NS, is needed to create 600 milliliters of solution? So we've got the 4 and 15 dilution. The 4 represents serum, or in this case, blood. The 15 represents total parts, or total solution. So on the other side of this, we have the 600 milliliters. What does that represent?
Solution.
The total solution. Are we looking for the amount of blood? No, we're not. We're looking for the amount of NS. But if we find the amount of blood, could we find the amount of water from that? Yes, we could. So if we cross multiply and divide, 4 times 600 divided by 15 is what, 160? So we could find the amount of NS by taking 600 milliliters, total solution, minus the 160 milliliters of blood, which gives us 440 milliliters of water. The other way we could have approached that is we could have looked at, rather than the ratio of the dilution, the ratio of blood to total solution, we have total solution, so we're still going to need total solution. But we could look at the ratio of water, NS, to total solution. So the total solution is still going to be 15 parts here. From that dilution ratio, how many parts would the water be? Good, 11. Because if 4 out of the 15 were blood, 15 minus 4 leaves 11 parts that would be water. Remember, the water has to make up everything else. So now we can put in the 600 milliliters. I can cross multiply and divide 11 times 600 divided by 15 is also 440 milliliters. So we'll get the same answer either way. I'll leave it up to you to decide which way is simpler for you to deal with. Okay, so again, there's sometimes examples that we'll hit that don't fit in real well with that we can only do one way by rewriting that ratio. For example, we might have in a 3 in 10 dilution of urine in water, how much solution is created with 210 milliliters of water? So we've got that 3 in 10 dilution. Now the 3 represents serum. In this case, that would be the urine. And the 10 represents total parts, total solution. How much solution is created? So we are looking for the amount of the total solution. Does the 210 milliliters describe the urine? No. So we are missing that number. So again, we are missing both numbers on this side of that proportion. So we cannot use that ratio. We can't use the dilution in its pure form. Now we're trying to find the total solution, so we're going to keep that part. And what we're going to put up here, of course, the only other part that we have that we could look at is the amount of water, the saline. So we still have 10 parts total solution. How many parts of that is going to be the saline? 7. Good. 10 minus 3 leaves us with 7. So now on the other side, we're still looking for total solution. We have the 210 milliliters, which does describe the water, the saline. And so we can cross multiply. 10 times 210 divided by 7 is 300 milliliters of total solution. These dilutions are used for a couple of different things. And we use them for diluting down. I mean, we did that, the mixture formulas in the last unit, where, you know, how much of the 15% do you mix with how much of the 35% to get 20% or whatever. Dilutions is one thing that can be done with that. Let's say we have a 30% solution. We perform a 1 in 4 dilution on that solution. Find the new concentration of that solution. So if we have a 30% solution, now remember, going back to what we did before, that 30% solution contains a certain amount of active ingredient, and then the rest of it is, you know, most likely saline, a neutral substance. So let's pick an amount. We don't have an amount of it given, but in order to do this dilution at this level, we're going to pick a volume. And to make it easy on ourselves, I'm just going to pick 100 milliliters of the 30% solution. So what that means is, in that 100 milliliters, it contained an active ingredient, a medication, serum, equal to 0.3 times 100 milliliters, or 30 milliliters of serum. So that's just a review from our last unit, where the amount of the active ingredient or the amount of medication is the concentration times the volume. So now let's look at our dilution here. We have that 1 in 4 dilution. And the 1 is the serum, but not the actual amount of serum. The 1 here is the concentrate. So in this case, the 1 is the 30% solution. And the 4 is still the parts of the total solution. Now again, I realize this 100 milliliters of volume, I just picked it completely out of thin air, but we can still use it to complete this. So if we had that 100 milliliters, how much total solution would we have? Well, 4 times 100 divided by 1 would be 400 milliliters of total solution. So we have now created 400 milliliters of solution by diluting that down. Now what I wanted to find was the new concentration. This new volume, the 400 milliliters, is kind of meaningless because we made up the 100 milliliters up here. But we can still use it to find the concentration. Have I added any medication, any serum to this? No. All we have added is saline, non-medicinal, non-active ingredient. So what that means is we still have only 30 milliliters of medication in our 400 milliliters of solution. So what we could do is we could solve that. 30 milliliters of medication equals X, which is our concentration, times our total volume, which would be 400. Dividing that out, dividing by 400 on both sides, would give us 0.075. So X is 0.075, or that is a 7.5% concentration now. So by doing that 1 in 4 dilution, we diluted that solution from 30% down to 7.5%. And now again, like I said, I realize I totally picked that volume out of thin air, but it doesn't matter. We can pick whatever volume we have to there to work through the problem. The percents are going to stay the same. What we're concerned about is the concentration, or the percent. We'll look at those a little bit more next week. For right now, let's look at a testing application of this. Let's say that we have a blood glucose meter that has a limit of 800 milligrams per deciliter. And we have a patient, we'll say a sample of blood, that exceeds this limit. So basically, when we go to test this sample of blood, the meter won't read it because it's off the limits of the meter. In fact, in many cases, even if you test a sample of blood and you're getting something in the high 700s, it's getting close to the limit of the meter, it would be a good idea to go through this process just to make sure you weren't actually exceeding the meter's limit, and it was just giving you that false reading. So what we are going to do is we are going to dilute 30 milliliters of blood with 90 milliliters of sterile water, of NS. So now we retest the blood, and we get a new reading of 262 milligrams per deciliter. Now I realize that would be a pretty high reading even without diluting the blood, so this person's in trouble. But let's take a look. What is the real reading? The true level of this blood sample. Well, the first thing we have to do here is we have to figure out the dilution. And remember, dilution is the concentrate, in this case the blood, compared to the total solution. So as I create this ratio, what goes on top to represent the blood? $30 milliliters. Good. What goes on bottom to represent the total solution? Be careful with this one. There we go. I had a couple people say 120. Yes. We have the 90 milliliters of water, but we also have the 30 milliliters of blood still. That has to be the total. We have to add those together. So that is 30 milliliters over 120 milliliters. Milliliters cancels out. That'll reduce to a 1 in 4 dilution. So that 1 in 4 dilution ratio can also be used to convert the reading. This reading here in the meter of the diluted sample of 262 milligrams per deciliter, is that smaller than the true reading, or is that larger than the true reading? Smaller. So we are going to put it with the smaller of these two numbers. The 1 is the smaller number. So we're going to put the 262 with the 1. And now we can cross multiply and divide 4 times 262 divided by 1 should give us, what, 1,048? Yes. 1,048 milligrams per deciliter. So that use of that dilution to convert readings is actually a pretty handy tool. Let's say that we do after a 2 in 5 dilution of urine in water, the meter reads 410 milligrams per deciliter. Find the true level. So we have that 2 in 5, that's a dilution, but it also is the conversion in our reading. Once again, the 410 milligrams per deciliter is a diluted reading, so that'll go on top, and you'll cross multiply and divide to get the other reading, the true level, which is what, 1,025, I believe there. Now we're down to under a minute here, so before you guys cut off, page 130 to 132 in the book, problems 1 through 37, the odds, deal with dilutions. So we will talk a little bit more about dilutions to start out next week, and then we're going to spend the next 2 weeks before spring break lecturing on dosage calculations. 1 more week of lecture actually after spring break. And then we will have the second Friday after spring break will be our unit test. So we do get 1 lecture after spring break before we jump into a test. Guys, have a good weekend.